Hi everyone, today we're going to study Green's theorem. Let capital C be a positively oriented, piecewise smooth, simple, closed curve. And let capital D be the region enclosed by the curve. Green's theorem states that a line integral around the boundary of the plane region capital D can be computed as the double integral over the region D, where the path integral is traversed anti-clockwise. In symbol, we write like this: the line integral over C, P dx plus Q dy is equal to the double integral over D, partial derivative of Q with respect to x minus partial derivative of P with respect to y, d capital A. This is our working formula. Example 1. Use Green's theorem to evaluate line integral xy dx plus x squared y cubed dy, where C is the triangle with vertices 0, 0, 1, 0, 1, 2 with positive orientation. First, let us write the formula of Green's theorem. Now, let us collect the values of P and Q. Let's begin with the P, and we write here xy. This is the function with the dx. Then, we write the Q. We write x squared y cubed. This is the function with dy. Let us now substitute these values in our double integral formula. Now let us evaluate the partial derivative of x squared y cubed with respect to x, and that becomes 2x y cubed minus partial derivative of xy with respect to y. So we write here x. Now let us draw the triangle. The vertices are 0, 0, 1, 0, 1, 2. Take note here that the line which is corresponding to the hypotenuse has the equation y equals 2x. We can get this equation using the two-point form of the line. We can observe here that x is between 0 and 1, while the y is from 0 to 2x. Let us redefine our d of a. We change this to be dy dx. And then let us write the corresponding limits of the double integral. For the first integral, that is for the dx, we write here from 0 to 1. And for the second integral, corresponding to the dy, we write here from 0 to 2x. Let us start doing the integration starting from the inner integral. So we have the integral of 2x y cubed minus x. This is with respect to dy. The integral of 2x y cubed dy is 2x times y raised to 4 all over 4 minus integral of x with respect to y is xy. We will integrate this with respect to 0 and 2x. So this 2 and the 4 can be simplified into 1/2. So we write here x over 2 times the quantity 2x raised to power 4 minus 0 raised to power 4 is simply 0. Minus, for the xy, it becomes x times the quantity 2x minus 0. Simplifying this further, the first group becomes 8x raised to 5 minus 2x squared. Let us now integrate with respect to dx. So the 8x raised to 5 becomes 8 times x raised to 6 over 6 minus the 2x squared becomes 2 times x cubed over 3. We evaluate this from 0 to 1. Take note, this 8 over 6 becomes 4 over 3. So the x raised to 6 becomes 1 raised to 6, which is 1, minus 0 raised to 6, which is 0, minus this 2/3 we write here outside the x cube, and then this x cube becomes 1 cube, which is 1, minus 0 cube, which is 0. The 1 minus 0 is simply 1. We simplify this further into 4 over 3 minus 2 over 3, and the final answer is 2 over 3. Example 2. Use Green's theorem to evaluate line integral the quantity y raised to 4 minus 2y, then dx, minus the quantity 6x minus 4x y cubed, then dy, where C is a rectangle with vertices 0, 0, 6, 0, 6, 4, 0, 4. We write the Green's theorem formula. Let us collect now the values of P and Q respectively. Let's begin with the P. That is the y raised to 4 minus 2y. That is the function with the dx. Then the Q, the negative of the quantity 6x minus 4x y cubed. We include the sign in here. This is the function along with the dy. So we simplify this further into negative 6x plus 4x y cubed. Let us substitute the values in the double integral formula. Let us now evaluate partial derivative of negative 6x plus 4x y cubed with respect to x. And the answer will be negative 6 plus 4y cubed minus partial derivative of y raised to 4 minus 2y. So we have 4y cubed minus 2. If we remove the grouping symbol here, we can combine these two functions into a single and simple one, and that is negative 4. Now let us draw our rectangle. The vertices are 0, 0, 6, 0, 6, 4, 0, 4. We redefine now our double integral formula. The d capital A becomes dy dx, and then let us write the limits of integration. For the first integral here, the outside integral, that is with respect to dx, so the limits are 0 and 6 respectively. For the inner integral, that is with respect to dy, the limits are from 0 to 4. Since negative 4 is a constant, we can move this outside the integral signs. So it becomes like this. Now let's begin our integration with respect to the inner integral, with respect to dy. So we have here the negative 4 times the integral from 0 to 6. The integral of dy is simply 1. Then we evaluate this with respect from 0 to 4. We simplify this further into 4 minus 0, and this becomes 4. This 4 is a constant, so we just multiply this with the negative 4 outside. We simplify this further into negative 16 times the integral from 0 to 6 dx. Let us integrate further. The integral of dx is simply x, So we copy the negative 16 here. We evaluate x with respect to the limits of integration from 0 to 6. So the x here becomes 6 minus 0, which is 6. And this 6 is multiplied to negative 16. So we have this negative 96. This is our final answer. Today, we're going to study Gauss divergence theorem. Let capital E be a simple solid region, and capital S is the boundary surface of E with positive orientation. Let capital F be a vector field whose components have continuous first-order partial derivatives. Gauss divergence theorem states that the surface integral of a vector field over a closed surface, which is called the flux through the surface, is equal to the volume integral of the divergence over the region inside the surface. In symbol, we write like this: double integral over S, capital F dot N ds is equal to triple integral over V divergence F dV. This is our working formula. Example 1. Using Gauss divergence theorem, evaluate double integral over S capital F dot N ds, where capital S is any closed surface enclosing a volume V, and capital F, or the vector F, is equal to 2xi plus 3yj plus 4zk. Let us write our formula for the Gauss divergence theorem. For step 1, let us evaluate divergence F. The vector F is given as 2xi plus 3yj plus 4zk. So divergence of F is this: partial derivative of 2x with respect to x plus partial derivative of 3y with respect to y plus partial derivative of 4z with respect to z. Evaluating the partial derivatives respectively, we have now 2 plus 3 plus 4. So the sum here is 9. This is the divergence F. Step 2, we substitute the value of div F and evaluate. So we copy the triple integral formula. Let us substitute the value of div F. Since 9 here is a constant, we can move this outside the triple integral. Evaluating now the triple integral over E of dv, we have now this 9v. This is the final answer. Now let us take note that for any vector point function capital F, divergence of curl F equals 0. Example 2. Using Gauss divergence theorem, evaluate double integral over S vector capital A dot N ds, where capital S is any closed surface enclosing a volume V, and vector A equals curl F. Let us write the Gauss divergence theorem formula. Step 1. let us now evaluate divergence A. In the problem, it is given vector A equals curl F. So we take divergence A equals divergence of curl F, and this is equal to 0. Step 2, we substitute the value of divergence A and evaluate. We copy the triple integral formula. The div A is equal to 0, and we substitute it here. Because of the 0, the triple integral is equal to 0. This is the final answer. Example 3. Using Gauss divergence theorem, evaluate double integral over S vector capital A dot n ds, where vector capital A equals 8xzi minus 3y square j plus yzk, and capital S is the surface of the cube bounded by x equals 0, x equals 2, y equals 0, y equals 2, z equals 0, and z equals 2. Let us write the Gauss divergence theorem formula. Let's begin step 1. We evaluate divergence A. We copy the value of A below here, then let us evaluate divergence A. It becomes like this. Partial derivative of 8xz with respect to x plus partial derivative of negative 3y squared with respect to y plus partial derivative of yz with respect to z. Evaluating now, we have 8z minus 6y plus y. We can see here that we can combine the negative 6y plus y. So the final answer, 8z minus 5y. For step 2, we substitute the value of div A and corresponding limits of integration, and then evaluate. We write the triple integral to be like this. The dv here is now changed into dx, dy, dz. The div A, we get the value from step 1, the 8z minus 5y. For the first integral here, we write from 0 to 2, and this is with respect to the limits of z. The second integral, the limits are from 0 to 2, and this is with respect to y. And the innermost integral is from 0 to 2, and this is with respect to dx. Now, let us begin the integration, starting with the innermost integral. So the integral of 8z with respect to x is 8zx minus integral of 5y with respect to x is 5yx. Now, let us evaluate this with respect to the limits from 0 to 2. So we have now the first group with respect to number 2 minus, we evaluate the same function with respect to 0. Look at our second group here. Because of that 0, this will be cancelled. We can simplify the first group into 16z minus 10y. Now let us evaluate again the integral from this point. So the integral of 16z with respect to y will be 16zy minus integral of 10y with respect to y will be 10 times y squared over 2. We can cancel this 10 and 2, so we have 5y squared. Let us evaluate this with the limits of integration from 0 to 2. And it becomes like this. The first group, we evaluate the function with respect to the value 2, minus the function is evaluated with respect to 0. In the second group, because of the 0, we can cancel this out. Then let us simplify the first group. Now it becomes 32z minus 20. Let us now integrate the final integral. So the 32z with respect to z is 32 times z squared over 2 minus integral of 20, that is a constant, with respect to z. So we have 20z. We simplify 32 by 2, we have 16 z squared minus 20z. Let us evaluate this with respect to the limits from 0 to 2. We evaluate the function with respect to 2, that is for the first group, minus we evaluate the function with respect to 0, that is for the second group. In the second group, because of the 0, this will be cancelled. Then we simplify the first group. So we have this 64 minus 40, and we have 24 as the final answer. Today, we're going to study Stokes' theorem. Let capital S be an oriented smooth surface that is bounded by a simple, closed, smooth boundary curve, capital C, with positive orientation, and let capital F be a vector field. Stokes' theorem states that the surface integral of the curl of a function over a surface bounded by a closed surface is equal to the line integral of the particular vector function around that surface. In symbol, we have this formula. The line integral over C, capital F dot dr is equal to double integral over capital S, curl F dot n ds. This is our working formula. Example 1. Using Stokes' theorem, evaluate the line integral capital F dot dr, where capital C is any closed surface enclosing a square region of the x equals 0 plane, bounded by the lines y equals 0, y equals 2, z equals 0, z equals 2, where vector f is equal to 2zyj minus 4yzk. Our step 1 here is to evaluate curl f. Given is the vector f equals 2zyj minus 4yzk. For the curl f, this is equal to del cross product capital F. And this is equal to the 3 by 3 matrix. The first row are the components I, j, k. The second row for the partial derivatives with respect to x, with respect to y, with respect to z, respectively. The third row is for the corresponding functions for the components I, j, k. So we have here 0, 2zy, negative 4yz. With respect to determinants, it becomes like this. For component I, we have this partial derivative of negative 4yz with respect to y minus partial derivative of 2zy with respect to z minus, for the component j, multiplied partial derivative of negative 4yz with respect to x minus partial derivative of 0 with respect to z plus the component k multiplied partial derivative of 2zy with respect to x minus partial derivative of 0 with respect to y. Simplifying this now, we have the quantity negative 4z minus 2y multiplied by I minus quantity 0 minus 0 multiplied by j plus the quantity 0 minus 0 multiplied by k. So we can simplify this further into the quantity negative 4z minus 2y multiplied by I. Now step 2, let us use the Stokes theorem. We have this formula. Substituting the corresponding values, we start with the curl f, that is the value we derived from step 1. So we have now in here. The ds, we write here dy dz. Now for the limits of integration, the first integral here, we write from 0 to 2. This is corresponding to dz. The second integral, we write the limits from 0 to 2. And this is with respect to dy. We just copy this dot n. Now, we let n equals I. That is to conform with this component I in here. So the n becomes I. Now, we evaluate this value of curl f dot I. So we have now this quantity negative 4z minus 2y dot 1. And we can simplify this further into negative 4z minus 2y. Now let's begin our integration in the inner integral. So the integral of negative 4z with respect to y is negative 4zy minus integral of 2y with respect to y is 2 times y squared over 2. And we can simplify this further into negative 4zy minus y squared. Now let us evaluate this with respect to the limits from 0 to 2. So the first group will be the evaluation of this function with respect to 2 minus the second group. That is, we evaluate this function with respect to 0. Look at the second group. Because of the 0, we can cancel the full second group. Now let us simplify the first group. So the first group becomes negative 8z minus 4. This is now the new function. Let us now get the integral of this function with respect to z. So the integral of negative 8z with respect to z will be negative 8 times z squared over 2 minus integral of 4 with respect to z. This is a constant, so we write 4z. We simplify this part into negative 4z squared, then we just copy negative 4z. Let us evaluate this with respect to the limits of integration from 0 to 2. We evaluate this function with respect to the number 2. This is now the first group. Minus, we evaluate this function with respect to 0, and we have the second group. Looking at our second group, because of this 0, we can cancel this out. Then we can simplify the first group. It becomes negative 16 minus 8, so the final answer is negative 24. Example 2, using Stokes' theorem, evaluate line integral over C, capital F dot dr, where capital C is any closed surface enclosing a rectangular region of the z equals 0 plane, bounded by the lines x equals plus or minus 2, y equals 0, y equals 3, where vector f equals y square I plus x square j. For our step 1, let us evaluate the curl f. The vector f is given as y square I plus x square j. So the curl f is given by this formula, del cross product v. So this is equal to our 3 by 3 matrix. The first row for I, j, k. Second row for the partial derivatives respectively. For the third row, we write the corresponding functions for the I, j, k. So we write here y square, x square, and 0. Now, simplifying this using determinants, we have this expression. For the component I, we have this partial derivative of 0 with respect to y, minus partial derivative of x squared with respect to z, minus the component j multiplied this partial derivative of 0 with respect to x, minus partial derivative of y squared with respect to z, plus for the component k, this is multiplied by the partial derivative of x squared with respect to x minus partial derivative of y squared with respect to y. Simplifying this, we have this the quantity 0 minus 0 multiplied by I minus the quantity 0 minus 0 multiplied by j plus the quantity 2x minus 2y is multiplied by k. Because of the zeros, this expression is now simplified into the quantity 2x minus 2y multiplied by component k. Step 2, let us now use the Stokes theorem. And the formula is written here. Let us now substitute the corresponding value for the curl f. Let us modify the ds and let us specify the limits of integration. So we have like this. The ds becomes dx dy. The curl f is here, dot n. For the limits of integration, the first integral has limits from 0 to 3. And this is with respect to the y. The values are here. The second integral has limits from negative 2 to positive 2. And this is with respect to the values of x in here. Of course, this is with respect to the dx. Now, for this n, we let n equals k. We will write this as k so that it will be uniform with our component k. So it becomes like this. So the curl f dot k. So the value will be the quantity 2x minus 2y multiplied by 1. We can simplify this into simply 2x minus 2y. Now let us start evaluating the inner integral. Integral of 2x with respect to x will be 2 times x squared over 2 minus integral of 2y with respect to x, that will be 2yx. We can simplify this portion into x squared minus 2yx. Then we evaluate this with respect to the limits from negative 2 to positive 2. So the first group will be, we evaluate this function with respect to positive 2. It becomes like this, minus the second group. That is, the function is evaluated with respect to negative 2. Now let us simplify both groups. So we have here 4 minus 4y minus the group 4 plus 4y. We can combine the two groups, and the simplified form will be negative 8y. So we'll get the definite integral from 0 to 3 of this negative 8y dy. The integral of this negative 8y will be negative 8 times y squared over 2. And we simplify this into negative 4y squared. Let us evaluate this further with respect to the limits from 0 to 3. The first group is to evaluate this function with respect to 3 minus the second group. That is, we evaluate this function with respect to 0. For the second group, because of the 0, we can cancel the whole second group. Now we simplify the first group into negative 36. This is the final answer. I hope you learned something from this video. See you again next time.